We want our AI models to perform really well, and they can perform really well. Like, you can get them to perform at 100% accuracy for the data that it's been trained on. But that brings a problem with it. A lot of the value with AI models is that they can generalize. Their ability to get correct answers from input data that is never seen before is kind of an important aspect. Although if you don't need that, then you could happily overfit all you want. As long as you have all the data and all the possibilities, you can make an AI model that will capture all that meaning, and it will overfit to the maximum. And this could work for your use case. However, in a lot of the cases as well, we might not have 100% of the data. Not all the data is there. And that is for the majority of AI and machine learning applications. So for those AI applications where we don't have all the data, which really is mostly all AI applications today, for the most part, we have a problem of underfitting and overfitting, usually more on the overfitting side. So if we look here at the screen, we've got ourselves 3 diagrams that we have. One that's underfit, so we see that it captures a good population of our targets here, which are the circles, but it also captures a lot of the non-targets. All the way on the other side here, we see an overfitted model where it captures every single target to 100%. And it also avoids all of the non-targets. Nicely overfitted, and it was able to capture all the data and features in that model, and it's 100% correct. However, if you give it input data that it's never been trained on, it's very likely that it can hit into a zone. One of these targets it'll be in a zone it'll miss. Like it'll have a probability miss here. There are a lot of approaches that you can take to improve the accuracy of your model. And we will go over each of those, my favorite ones, and we'll be able to approach a solution that looks more like this, where we fit. It might not be the perfect use case, but it gets it more right than not. When we're training AI models, we want to make sure that it has the highest possible accuracy. When we give it information, we want it to be able to give us a highly accurate result at the end. What is its predictions? What are its assessments? We want it to be as accurate as possible. However, we don't have enough data to give it perfect accuracy for all scenarios. Usually with an AI model, we don't have the whole picture. We have a lot of the picture, and so we can give that data to an AI model to train and fit, and so we need it to generalize enough so that way it can capture the highest possible accuracy, especially for data that it's never seen before. So there are a lot of tricks to be able to reduce the underfitting and overfitting approaches. Mostly we're going to be talking about overfitting. We're going to start off really quick by talking about one easy option here is to modify your existing data. Okay, so let's see here 1 second. Let's say we have a bunch of data here, right? So say we have just a series of sentences, and all these sentences are pretty static. Something we can do is reorganize some of the words in the sentences. We can even add misspellings and things like that in the sentence. Like say we might want to change the E to an A, or maybe incorrect grammar. And now that will be a new entry. So you've just augmented your data. We can also do synonym replacements. So we could do things like that. So instead of noisy, we have loud. So you can synonym replacements. So basically we're augmenting our data. We're taking the data that we have, and then we're giving it more examples of that data point. This does require some extra work up front, so you're mostly dealing with the data in this case rather than optimizing the model, which is where the fun part comes in. But there is some fun in the data. There's some fun in the data too, because we don't have to do this by hand. We can just grab a dictionary and programmatically go through all the sentences, and then just randomly update 1 or 2 of the words in the sentence. So we can do this algorithmically, and now we've got a lot more training data. You can do the same things with image input as well. One of the common approaches is to shrink the image size or expand the image, rotate the image. You can like sort of, what do you call it? You can shrink the image in one dimension or the other, or you can sort of skew it in a third dimension. Data augmentation in this case, not only will it help reduce overfitting, however, it will also improve the accuracy overall, because you're giving the AI more examples on what it needs to know. When we're building an AI model, we want to make sure it performs as best as it possibly can. And the good news is there's a lot of approaches that will significantly increase the accuracy of the output. And this is all about overfitting and underfitting is a common challenge. Basically, where you're trying to target the most accurate output possible, and on either side, you're optimizing for a shape that's kind of tricky to get to. The good news is there's a lot of approaches to help that. And there's some examples here that I want to walk through. For example, early stopping. That's the easiest one. So as you're training a model and providing it all the input data, and you're back propagating and you're optimizing the layer weights, you can just stop before you don't need to keep going. Because you can train it forever and ever and ever, and then you'll get diminishing returns on the accuracy because the loss is reduced to such a small level that it can't really optimize any further. But you can stop before that, which will have a model that has more general shape. It won't create outlines across all of your features. And so it's kind of the easiest option, although it's a little challenging to keep consistent. Perhaps you can just early stop once you've measured. For every epoch, for example, you could measure the accuracy output, and if you hit a target accuracy, you can move forward from there. Or you could basically save the weights every single time for every epoch, and then only... I guess when you're saving the weights file, you could also append like the accuracy number in the file name, something like that really easily. So then you don't have to worry about stopping early. You'll just find the right number so you can train through. I like that approach. I've used that one before. Another really common one is regularization, which it sounds tricky, but it's actually fairly simple. It's when this only at training time. You don't need this during inference time. You'll be modifying the output of the loss function by the sum or the mean of all the parameters in a layer. So in this case, what we're looking at here, we have 3 matrices. So like if we break it down to like a simple approach, basically the idea is we have ourselves a matrix, and it's going to take all the parameters in that matrix, all the different units, or the weights they're called, and it's going to sum them into a single number, and it can either do that with a square or an absolute value. That's the difference between L1 and L2. And then when the loss is calculated, it can be applied to the loss during back propagation. It will make adjustments from that perspective. Now what that does is it kind of like this flattening of the gradient. It kind of smooths it out. It reduces spikes in the gradient. Because what you want is like a nice smooth gradient. You don't want something that's gonna bubble up and hit like a ceiling or a giant point. You want kind of like a smooth. You don't want like rigid values or super spiky values that go off into infinity. You want nice smooth gradients for every layer. And so what you can do is help smoothen out that process by attaching regularizers to every single matrix that's involved in the training process. And this is only done during training time. You don't need this during inference time because it's only leveraged in the loss, which is going to be applied during back propagation to apply adjustments to the layer weights. As it's learning, it's the learning process. Here's a couple quick easy tips for you if you are training an AI model and you want to prevent overfitting and underfitting. You want your AI model to be as accurate as possible across data is never seen before. As we're training AI models, we don't have all the data. If we had 100% of the data in all of existence, we can train the perfect AI model. But we do not. We only have slices and snippets of data, and we only have so much compute power to go around. So to get the best performing models, we have to use some tricks to reduce the training time and increase the accuracy. Here's a couple of the tricks. We've already gone through a few of them. One of the quick and easy ones is dropout. I like this one because it's super easy. It's only done during training time. The idea is for every single matrix that you have in your model, you can insert a dropout layer, which is going to randomly deactivate some of the layer weights, the downstream layers. Basically, a dropout is going to be a matrix of the difference between 0 and 1, or it could be all 0, like a whole bunch of zeros, a bunch of ones, and randomly distributed in a layer. So what it's going to do is sort of like force downstream layers to learn things a little differently. It's an easy option. It's a single line change in your application. For the most part, it looks like this. You would just say, here's the dropout, then you'd add that layer into your model, and then you'd say the percentage or the rate, right? So if you said 50%, that would mean it would lose 50% of the neurons above, which sounds like a lot. So this is part of like the hyperparameter tuning aspect. You can add a little bit of dropout to reduce the overall overfitting problem. And then during inference time, this layer is completely ignored during the matrix multiplication process. Yeah, that's why I like dropout. It only applies during training time and not during inference time. So it's pretty straightforward and easy option. It does a pretty good job. I like these little easy tricks. Oh, there's a problem though, because you might need to increase your layer weights and then modify your learning rate. So there's some trade-offs, and then you just have to sort of see how it goes from there. So maybe start with a little bit of dropout and then increment from there, but you might have to increase the layer weights, the number of units that you have in each layer. So while it's easy with dropout, it's not a for free thing. You still have to do a little bit of extra work. There is an ideal AI model where you have the least amount of computation required to have the most benefit. So you can have a really small model that achieves a high accuracy. Now, while that's like the best possible outcome in the real world, it's generally pretty hard to get there. So we need to use a bunch of tricks to make our AI model perform better. Early on in the training cycle, when we are building our first model, we might have a large amount of layers and weights, the number of parameters or units in every single layer. That'll allow the AI to learn a lot because it has a lot of options for it to understand as you're passing in data into the model. However, that can easily lead to overfitting. While that can be useful if you have all the data, we don't have all the data. We only have a small picture of the data. So we need the AI to do the best it possibly can at generalizing. So something that we can do, which is an easy option, which improves the overall performance of the model in terms of its capability of generating outputs and training speed, is we just reduce the complexity of the model, having fewer parameters and fewer weights or fewer layers. And just like all the science fiction shows say, the more data the AI has, the smarter it can get. So try to get your hand on as much data as possible. This is going to give your AI an extra boost, because if it had all the data, it would be able to answer all the questions. Today's AI algorithms completely have the capability to operate on a near perfect score. However, we don't have all the data, so try to get more data to help improve your accuracy. Another fun way to go about this is to create a bunch of different runs, or essentially a bunch of number of training events by cross-validation. Essentially is you're only going to take segments of your data and you're going to try to test that data across a variety of training cycles. For example, we'll run through a whole bunch of epochs on the data, but exclude chunks of data here. So you can see we're excluding certain chunks of data. And at the end, we're going to get models that perform varyingly, like they will perform differently because you've trained them on different information. However, part of your data set is going to help the model generalize a little bit better, only targeting certain aspects of your data. So it's got a fancy name to it, it's cross-validation, but it really just means that we're going to be training on a subset of data and you're going to try to segment that over a variety of subsets. Another approach is to reduce the magnitude, the maximum value of every parameter in a matrix. So if that model's like increasing like 10, 20, 100, you might want to sort of cap that at maybe 50. And so that will prevent the gradient from hitting a very high value. This will allow the model to better generalize. However, you are going to be getting sort of like a capping or a clipping of the gradient. Less ideal depending on your use case. So it might be an interesting strategy. However, as you're training a model, it's going to be approaching a certain point, you can sort of clip that and it's going to look more rigid depending on the number of dimensions you have. Like it's easy to like imagine 3 dimensions, but you have more probably. But that is a good way. Weight constraints is a really good way to definitely generalize on that data. It will prevent overfitting and your model will be more capable and more generalized. We can augment that data. Since we don't have all the data, we don't have all the data. We have a good amount. However, if we want to train our AI model and have it perform better, we can use some tricks. One of the tricks is adding noise with noise injection. The idea with this, adding more to our data set, which will help the model sort of understand it'll allow it to see beyond what the possibilities are. So say for example, here, let's actually just take a look here. So we've got some sentences here. You can train it on say a whole bunch of gibberish, like a whole bunch of random maybe numbers there. You can also add a little bit of gibberish inside something that would be more concrete, but like you can add some of these things. And what it's going to do is it's going to sort of help force the model to learn better the important aspects of our actual training data, right? For every single sentence, for example. I like this one. This is pretty cool, but it's a very satisfying approach. I like, 'cause you don't have to go crazy. You can just add a little bit of noise here and there into all of your training data sets. It actually might be interesting to see if you added a lot of noise. What would I've never done that before. The AI will only see what you give it, which is, it doesn't know. It knows nothing. For example, if you just provided a bunch of data on input, it really doesn't know what's going on compared to the different aspects. So like any relationships, It won't know. You can, however, guide it a little bit better using pooling layers. And what that does is it helps cross-examine many correlations inside of the matrix. It's going to be creating a series of correlations between adjacencies in the 2D matrix, for example. You can even go into 3D matrices if you want. It can take boxes and generalize to a single point. This will help accelerate the learning of your model, but it'll also allow it to understand relationships due to proximity. This is really useful in, for example, images, because our images, they're in 2 dimensions, right? So it's pretty easy to say the pixel right below compared to the pixel above is going to have important meaning. So you can add that in, and the pooling layer will help this happen, as opposed to just fitting the entire blob of data in, which you can do. This also works with text input as well, although I would say it's less interesting, though it could work. So for example, if we had some text here, like comparing the word test and unfair might be on different levels or in different sets of the matrix, it might be able to cover that case. Or it might be able to compare the word unfair with studied, depending on the resolution of your pooling. It really is that simple. It's just taking the input matrix, wherever it is in the layer, and then it's looking at the XY coordinates, and then it's merging cells, usually through a sum or a mean, the average of the cells, and making a smaller matrix. It makes it sound so fancy with pooling layers and convolutional neural networks. For improving your AI model, there's a few fancy approaches that we can use to leverage to make a higher accuracy model. Some quick, cheap tricks, or even probably the cheapest trick is to use someone else's model that they've already trained. I think that's the easiest approach. I'll just use that one there, thank you. And then you win. You win. However, if you want to also add it, because you might have a unique data set that you want that model to be aware of, so you can use something called transfer learning, where you append a few extra layers to the end of the model, usually before the output layer, and then you train the weights in just those last 2 layers, and you freeze the upper layers. So as you're performing gradient descent, only the final 2 layers are actually being modified. That's probably the cheapest and easiest trick that you can use from a computational perspective, from a time to market perspective. You can use transfer learning. Another fun approach is the ensemble method, where you're going to take a bunch of models that are completely independent, and you're going to capture the output between each of them, and then you're going to average the output. That's it. It's really easy. They have all these fun, fancy names for AI that sound entertaining and complex, and like, oh man, that sounds complicated. But it really is. It's really straightforward. Really, the idea is we do have to figure out a way to distinguish between all the different varieties of methods that are available to us. So having an accurate terminology is important, though it makes it sound complicated when it really is quite simple. Your AI model can get a lot better by adding a few extra tricks. We've got more tricks here to talk about. We've got learning rate schedule. So as you're training your model and it's learning through back propagation and gradient descent, you can modify how quickly it's learning over time. You can change the rate of learning. This one's also fairly straightforward, where you just modify the learning rate, which is one of the largest hyperparameters that you could focus on. And the idea is you want to achieve the global minimum with a high accuracy output for the best possible generalization. And if you stick with a static learning rate, you're going to usually fall into a local minimum, which can be fine as long as you have enough weights and layers, but you're going to increase your computation costs, and it's possible to do overfitting. So something you can do, vary your learning rate over time. You can also randomize it to help it jump past a potential local minimum and approach a global minimum, which is going to be a better overall result. So that's a fairly easier hyperparameter. The second biggest hyperparameter that you can tune is your batch size. This is going to help reduce your overfitting significantly. The larger the batch size, if you have a batch size of 1, you're just going to be training on that 1 data point, and it's going to be able to learn every single data point that you provide it very well. And that's the best way to overfit a model. If you really want to overfit a model, make the batch size 1. If you want to generalize your model, make the batch size bigger, and that's going to help the model learn over a set of data points. So for example, you have a variety. Let's just take a look at some of the data here. If we train it on these sentences here, it's going to learn an average across those sentences as it's calculating the loss, and it calculates the loss on the batch. So that loss is going to look different, significantly so, especially during backpropagation. This is I would say, hands down, the easiest approach to hypertuning parameters. Hyperparameter tuning is to increase your batch size. Now, there's definitely some more hyperparameters that we can look at here, such as the model density, the number of units or parameters, which are also called the weights. We can change the activations that occur after every layer, number of layers. Another one that we can choose is the values of the weights at the initialization. Usually it's a randomized between maybe -2 and +2. You can randomize it to -10 and +10 for every single parameter in the matrix. You could also start with just ones. That might work, though I've always had better results starting with randomized numbers. Typically between -2 and +2, I've found the best outcomes when I have random layer weights, all the parameters and all the units. Even with the same data set, if you take a look at just the learning rates, the number of neurons, and the number of layers, you can see that you can get a higher accuracy output by just adjusting some of the data. Not the data, the hyperparameters. So we have the same data as before, but the hyperparameters you can just adjust. So for example, 3 layers, 512 units per layer, and a learning rate of 0.1, and you get 85%. But if you jump over here to the bottom one with a couple extra layers, and even though we have fewer weights or parameters with the number of neurons, you get a higher score. Since all of these are fairly arbitrary, usually when you're training, you'll have the option to do something called like auto ML, or just randomizing those hyperparameters and then running training over them to find parameters that work really well. When we're training our AI model, there's a few more tricks we have left. We have a handful of tricks that we can use to improve the accuracy of our model. Since the model learns exclusively on what you provide it, we have an opportunity to more curate that data. We don't have to give the model all the data that we have. We can give it just curated sets. So for example, we can change the kind of data that we are using when we're training it. We can exclude some of the data that's going to be noise. For example, perhaps you have a data set where you have location, like latitude, longitude, or maybe a phone number. That is data. However, it might be just kind of too much, right? It might be, the AI might be able to look at that and then it will use that information to generalize in a way that is actually counter to the productivity of the model. So you can just exclude that data. There also might be additional features which are kind of interesting that you might want to add into the model that might have a better overall outcome. We can go a step further when we're modifying our input data to provide fake data. You might have heard of those generative adversarial networks, right? That's where we have a bunch of random data, some noise, and we input that and we use that data as a penalty. For example, like, oh, don't go that direction, ignore this direction because it's like random fuzzy data. You can do that and it will help the model actually perform quite a bit. This is actually a pretty good approach, I would say, because you can choose how much random fake data that you add into the system. And you want to make sure that the model is able to recognize that random fuzzy data and it will learn to avoid it. Here, for example, we have on the screen some just random data that is, I typed in randomly on the keyboard, but you can get a better resolution on the randomness there. This data will be used to train the model and have it output sort of the opposite of the direction that you're looking to target. So you can use this as input data when you're training the model, and it will be able to recognize things like this. Because we don't have the full picture, I mean, technically, actually, we could add a permutation of every possible input, sort of randomized sentences to where all literature has ever been cataloged. Like, we can do that. We can create random sentences and eventually you'll get to a real sentence that is understandable. However, the amount of computation that you need to do that is going to be insane. So we can help a model get a little bit closer to its understanding by injecting a little bit of random data and then using that as the output to say, don't go that direction because that's not the direction we want to head in. Another interesting approach that we could use is curriculum, sort of a curriculum training model where we start with the easy, like maybe simpler examples, and then we graduate to more complex examples, and then advanced examples. And as we're training the model in that approach, it's possible that you can generalize better overall with a model. It is a neat pattern. I've not used it myself, but it could help improve a few accuracy points. And as we're modifying our training data and the input, we can add some noise into the input training. So we're actually helping maybe augment our training data. We have a good example training data set. For example, let's actually take a look at a sentence really quick. Okay, so say we've got this sentence here. This sentence is a pretty straightforward sentence. We could go in and add more sentences like this and maybe take a letter out here or there, or we can add a letter in. And what we're doing is we're adding some noise into the data. So we still have the original sentence, but we also have a sentence that is a close neighbor of it. And the level of randomization and the noise that you add into the system will help it generalize better so we don't have so much overfitting. This approach actually pretty closely similar to almost, I guess we've covered this one already. Noise noise injection. You can either randomize the input data, or after embedding, or the output data, you can randomize the output target as well by ever so slightly amounts. This will help generalize and then allow your model to perform a little bit better. There are a few final approaches that we can use to make our AI model that much better. And there's some examples here that I've never used before, but sound kind of interesting. For example, we can use stochastic depth, which is an approach where we randomly drop layers. We can drop entire layers. This would be during training time. Exclude certain layers depending on the training cycle. So you could have, say you segment your data into like 5 buckets, 5 different curriculums. You can exclude several layers during that training process, insert those layers back in, maybe remove a couple others and add them back in, and then sort of, it's like a shuffle approach. You add and remove matrices for different cycles of training. That's kind of interesting. I'm sure it will work and it'll actually help improve the accuracy of your model, but it is a lot of extra effort. You have to do a little bit more effort. Another approach here is data distillation, where it's more of a curation. So we take, you as a human will find the examples that represent the most general possible examples, like the really foundational examples that set the tone, what you're wanting the AI to accomplish. So you can do this, and a human will have to be involved, and this is a lot of the data scrubbing and cleaning process. You can create a curated set of data to have the model train on, sort of like a foundational information knowledge. So for example, you can have the foundational model fit pretty well on the foundational data that you provide it, and then you have the more fuzzy data that's over here, and then you can go back and train it again, maybe at a different learning rate, maybe with a different batch size. Just changing how we're training the model over time will significantly change the accuracy. Another approach is to use embeddings, which is super useful because what it's going to do is it's going to take where your model is really doing all of its learning outside of the embedding. It's going to be able to reduce the dimensionality overall. As you're inputting like a large amount of features, it can help reduce those into a smaller output matrix that can be that the main network will learn on. So this will increase accuracy, it'll increase performance time, so training is a little bit faster. And because there's fewer dimensions, it will be able to prevent overfitting, or at least significantly reduce it. And another trick here at the very bottom, the very last one, we have adding an epsilon to the input features, or the outputs as well. You can just sort of slightly tune, so that way if you have one data point, so like one item, and it might have a bunch of flags that are 0, you could instead of putting a 0 in, you could put a small value like 0.00001. Instead of 0, just replace it with an epsilon, which is just a small number. So it will prevent it, as it's inputting that into the matrix, it'll prevent the deactivation of neurons. And so it'll help smoothen the gradient, because that's all what we're looking for. We're looking to smooth that gradient, so that way we have a nice generalized picture, and the model will have a higher accuracy. When you're doing this, you can do it at training time. You might not need it for inference time, but you could also include it at inference time as well. You might also want to do that. So all of these things that we've gone over, all the hyperparameters and the tuning and regularization, early stopping, since we don't have all the data and we only have just this much of the data, we want to help the model learn better by expanding our data with synthetic information. And we also want to prevent the model from going too extreme in either direction or capping out. We want a nice smooth gradient for all of our layers. There's so many options. It's really hard to sort of pick which one. AI in machine learning is actually pretty straightforward, fairly simple, though the terminology just makes it feel like it's a hard barrier to entry. Really, each of these approaches are fairly simple and straightforward because we're just dealing with a matrix. It's a spreadsheet. You're just looking at a spreadsheet and you're taking the columns across the spreadsheets and all the rows and you're multiplying them on top of each other, and that's the main feature of AI. And so all the tricks that we discussed are just taking all those matrix multiplications and then just sort of shaping them a little bit better, so that way we get a nice generalized AI model at the very end.